We've already spent some time in Chapter 2 learning about statements and compound statements, and now we're going to move that analysis forward into predicates and quantified statements. So we often need to separate these statements into parts, much like we would separate declarative sentences in our English classes into subjects and predicates. So we're also going to be analyzing and understanding the special role played by words that denote quantities such as all or some. They're very powerful words in mathematics and especially in proofreading. The study of predicates and quantified statements is called predicate calculus. So we're going to start by understanding that we're talking about predicate calculus. And what we learned about in Chapter 2 was all about statement calculus. So what is a predicate? Well, it's very similar to what a predicate is in a sentence. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. So remember here, finite means countable, right? A discrete number, if you will. So finite number of variables, and the predicate becomes a statement when specific values are substituted for the variables. This predicate also has a domain. The domain of a predicate variable is a set of all values that may be substituted in place of the variable. A lot of this is going to sound like mathematical functions from algebra. We're going to have a domain. We're going to be able to substitute in different values from that domain to evaluate our predicate. It sounds very similar to functions. And hopefully it'll help us ease into our study of functions when we get out to Chapter 7. So let's see how this goes together. In the sentence, Yemi is a student at Howard Community College. Yemi is a subject, and is a student at Howard Community College is the predicate. In logic, predicates can be obtained by removing some or all of the nouns from the statement. So if we let P stand for is a student at Howard Community College, we let Q stand for is a student at, then both P and Q are predicate symbols. And notice we have moved from lowercase letters to uppercase letters. Uppercase letters indicate predicates that are quantified. And our lowercase are our simple statements that we use in Chapter 2. So if we said X is a student at Howard Community College, it is symbolized as P of X, right? P of X is a student at Howard Community College. So that domain here, X would be the set of all HCC students, right? That's our domain. But what happens if I remove another noun from the statement? Then we say X is a student at Y. And then we will symbolize this as Q of now two inputs, X and Y. And our domain has changed dramatically because our domain would be all students, that's the X's, at all schools. There are your Y's. We did not put any qualification on what the school is, so now all schools are valid. It could be that Johnny is a student at Miss Debbie's daycare school. That is a true statement. It could be that Johnny is a student at Shaker Heights Elementary School. Also a true statement. It could be that Susie is a student at Harvard University. also a true statement. So, what happens when we take out the nouns and turn them into part of our input is we open up our statement to be much, much broader in scope. And in the case that we have here, x and y are both predicate variables that take on values in appropriate sets now. Now you'll have to feed in a student and a school into our predicate statement in order to make a statement. So, before we move forward, we have to talk about all of the amazing symbols that we get to learn. And in this class, the one thing that you're going to find out about mathematicians is we are very good at finding abbreviations. So everything we do, pretty much, I feel like, has an abbreviation. We don't even write out the word therefore, we do 3 dots. So, I mean, if we're willing to abbreviate therefore with 3 dots, what won't we abbreviate? So let's talk about some of our most common abbreviations in mathematics so that we know how to use them. And we're going to be using them so much, you will use them from this section through the remainder of the semester. All of our proofwriting, all of it. So, let's start with talking about some background information. So a little bit of this comes from chapter 1, which we're not covering specifically. We're not going to go look at a section in chapter 1. However, if you wanted to go back in your e-text and read through this sections in chapter 1, you absolutely may. You'll find that I have integrated the material necessary from those chapters or those sections from that chapter into all of our other lessons. And here's one of them, a set. What is a set? Well, a set is a collection of elements. And typically, they usually share, right? They usually share some characteristic. And then mathematically, we have some very important sets. Sets that we talk about all the time. The first one is the set of all real numbers. All real numbers. When I write it, I will write an R with an extra leg. The text and the online homework will make it a bold R. That is a set of all of our whole numbers, our fractions, our decimals, our square roots. Essentially, it's any number that doesn't include an I. That is our real number set. So the numbers that include I are called complex numbers. And the way that we think about number sets is this way. We have this massive set of complex numbers. And complex numbers are made up of a real part and an imaginary part. You get a real plus or minus, depending on what your complex number is, and then another real number times I. The real number times I is our imaginary part. The other part is our real part. So within that large set of complex numbers, we find another large set, which is the set of all real numbers. In that case, all of the complex numbers that we had in the largest set, we just let 0 be the number in front of I, and so we're only left with a real part, and that's how we walk ourselves back from all of the complex numbers down to just real numbers. But we can also zero that in a little bit more with the next 2 sets. This Z, which I usually write, and I learned this from a student, do a 7 and then upside down backwards 7, and you get a perfect Z with an extra line in the middle. This is a set of all integers. Integers are whole numbers. So these integers are positive numbers and negative numbers and 0. So positive whole numbers, negative whole numbers, and 0. We can instead zoom in a little bit more by saying, okay, but what if I only want part of the set of integers? And we do have a couple of really special parts. If we have z plus, that is the set of positive integers only. Now bear in mind that does not include 0, it starts at 1. Likewise, we have z minus, which is the set of negative integers, which again does not include 0. There is a very special set that does include 0, and that would be the set of natural numbers, which looks like an n with an extra leg in the middle. That would be 0 and all of our integers in z plus. So typically instead of saying and, we'll just say 0 plus the set of positive integers. And what that means is now we can start at 0, and these are what we would typically call our counting numbers. 0, 1, 2, 3, 4, 5, 6. The only thing we don't have are negative integers. So you might think integers are maybe the next smallest group, but we're going to compare that with another group momentarily. And that is this set of numbers represented by a letter Q, and that is the set of rational numbers. These are the numbers that can be expressed as a ratio of integers. 4 divided by 3, -2 over 5. Those are rational numbers. And why are we not using R for rational? A couple of reasons. Number one, R is already taken, it's all the real numbers. And number two, we're dividing integers, which means we're finding quotients. So we use Q to stand for quotient. So all of our rational numbers are quotients. And the way that our integers and our rational numbers are related is really cool because our rational numbers are everything from like 1/2, 1/4, 1/8, 5/3, all of our ratios of whole numbers. But there is also something inherent about whole numbers themselves that also means they can be expressed as rational numbers. Think of the number 2. Can it be written as a rational number? The answer is yes. 2 divided by 1, right? Let's see here. Let's try -4. -4 can be written as -4 divided by 1, or even -8 divided by 2, right? Also rational numbers. So we find out that there's an infinite number of rational numbers between each integer set, which means there are more rational numbers in theory than there are whole numbers or integers. So in this case, our next largest set would be the rational numbers, and then our smallest set is going to be the set of integers. And again, within the integers, if you really want to, you can break it down into positive or negative or natural numbers. It's up to you. We won't see the natural numbers symbol in our other notes or on the homework, but I wanted you to see it in case it shows up in another class. So now we need to keep moving forward with some more information about how to describe elements in these special sets of numbers. So we say x, and we have this little sideways sort of curvy e. It says x and the symbol and then p of x. What that means is that x is an element in the set of p of x, or x is contained in. So if I were to say x is in z, that means x is an element of the set of integers. Or in simpler terms, x is an integer. It is contained in the set of all integers, which means it itself has to be an integer. So that's how we describe x is in the set of integers. X is an integer. If I were to draw the universal no symbol through it and say x is in, and then draw the line through it, it means x is not in the set of, in this case, real numbers, which means that x is not a real number, which means it has an I. It is a complex number. So it just means that x is a not real number. Well, I think that sounds a little awkward. X is not a real number. We're not going to be studying complex proofs, complex anything, any kind of analysis of complex numbers, because it is a special branch of mathematics and a very cool one. I highly encourage you to check it out if you've never looked at a complex analysis book. It's really fascinating. So I highly suggest checking out complex analysis. It's really cool what you can do with what we like to call imaginary numbers. So highly encourage those of you who are really mathematically minded to go check out a complex analysis course. The last symbol here, or last definition really, is this set builder notation. And it's a way for us to describe sets. And in this case, I have in my curly braces, which describes a set. It has to have curly braces. It says x is in the set S, and then it has a vertical bar, and then p of x. So you know there's some relationship between the two pieces on the left and the right of this vertical bar. What it's saying is x is an element of the set S such that p of x is true. That's what it's saying. X is an element in the set S such that p of x is true. So it just means that when x is in our domain, the predicate p of x is true. So let's see if we can figure out how to evaluate or answer questions about some of these set notations, some of our different kinds of domains. So let's let Q of n be the predicate. N is a factor of 8. What we want to define for this statement, this predicate, is the truth set. So what is the truth set? A truth set is a set of all elements of the domain D of x that make p of x true when they are substituted in for x. Sounds kind of like a domain, but it's a little more complicated than domain. It is the set of all elements from our domain that make the statement true or make the predicate true. So let's find the truth set of Q of n if the domain of n is in Z plus. Well, let's talk about what Z plus means first. Z plus is our set of positive integers. And we'll write that with here, right here. So this would be the set of all positive integers. Oops, there we go, integers. And so remember, Q of n is the predicate, n is a factor of 8. So what we're looking for here are factors of 8 that are also sets of in the set of positive integers. So what we're looking for the truth set, so our domain, right? Our domain is Z plus, it is the set of all positive integers, but our truth set says that we need to have only positive integers that are factors of 8. Well, there are two ways to get the number 8 by multiplying. We could have 1 and 8, or we could have 2 and 4. So in this case, our only numbers that we can include in our truth set, our only values are 1, 2, 4, and 8. Does that change if we change our domain? And the answer is I think it would kind of have to. Not necessarily, but let's see if it does. So now, instead, let's think about our domain being Z, which is the set now, not of all just positive integers, but all integers, all of them, which means positive and negative and 0. So our domain now is a set of all integers, and now our truth set, right? Our truth set involves not only the positive integers, but the negative ones as well, because -1 times -8 is still 8. So we would have plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. You can write it that way, or you can write out the set -8, -4, -2, -1, 1, 2, 4, and 8. It doesn't matter which way you choose. When you try to do this in your 7-gauge web assigned homework, if you can't find the plus minus button on the given, I don't know how to explain it. It's not really a calculator, but it's like a toolbar. So there's a little toolbar to help you enter in your answers. If you can't find the plus or minus button on there, just write them out separately. It won't take that much longer. Okay? And Cengage should accept either one. So beyond domain, and now all of these fun new symbols for domain, and is an element of, and is in a set, all of these things, right? We also need to define something we call quantifiers. Quantifiers are indicative of quantity. How many are we talking about? Are we talking about all of them, or are we only talking about some of them? So the first quantifier we're going to talk about is the one that is for all. So first things first, let's look at our definition of quantifiers. They are words that refer to quantities such as some or all and tell us for how many elements a predicate is true. How do we write these things? Well, let's see. We now have this upside down A. And the upside down A, I told you we have an abbreviation for everything, right? The upside down A is what we call our universal quantifier because it is read as any of these different phrases: for all, for every, for any, for each, or given any. That means all. We're talking about all. This is when you use a universal quantifier, you're doing an all or nothing kind of thing. You're being very absolutist. You were talking about all. Okay, it is all. That is why it's also universal. So when we talk about something that is universal, that means it's applicable to all. That's what we mean here. Universal quantifier means all of them. So we could say something like every human being is mortal. We can write that as for all human beings X, X is mortal. Now, if we wanted to take it just another step further, so we said for all human beings X, X is mortal. If we wanted to take it one step further, if we let H be the set of all human beings, then we can symbolize the statement as for all X in the set of humans, X is mortal. So the way that we read this is for all, right? For all X in the set of humans, X is mortal. So if we let Q of X be a predicate and D be the domain of X, then we can now define a universal statement. So, what is a universal statement? A universal statement is a statement of the form for all X in the domain D, Q of X is true. So, for all X in D, Q of X. I'll highlight there for us. It is defined to be true if and only if Q of X is true for every X that is in our domain, and false if and only if Q of X is false for at least one X in our domain. If we can find even one time where an element in our domain makes our predicate false, our entire statement is false. And that one false proof, right? That one element that proves our statement false is called a counterexample. It is a counterexample. So we only need, right? We only need one counterexample to show that a universal statement is false. And remember, that's because this is an absolutist statement. It says for everything, everyone, every being, every whatever we're talking about. And if only one of those elements says, not true for me, then the entire statement is wrong. Because now it's no longer about 100% of the elements in our domain. And if it's not about 100% of them, it is no longer universal. So we only have to find one counterexample if we want to show that a universal statement is untrue, right? If it is false. Our quantification in this case can also be implicit. It says qualification, I meant to say quantification. Our quantification can also be implicit. And this is something more in the way that we would say it in our sort of everyday language. For example, if a number is an integer, then it is a rational number. It doesn't include the words any or each or all or every, but it does include the article a or an, right? An even number. This is an example of what we call an implicit universal quantifier. So we can write this one in a really cool way because this is something that we haven't seen yet. And that is says, for all x in the set of real numbers, if x is an integer, then x is rational. So I just threw at you a whole bunch of these brand new symbols, right? We have real numbers, we have integers, right? We have reals, we have integers, and we have rationals. Remember, rationals are quotients of integers. And so if we look at our domain, it says for every real valued x, if it is an integer, then it is also rational. That's what this same statement is saying with all these symbols. So why is our domain not just integers if we're talking about integers? Well, that's because our claim is that it's an integer. So we have to sort of zoom out on our domain. So we would have for all x in the set of real numbers, which is all of the numbers that we're going to be looking at. If x is an integer inside that set, then it is also rational. And this is what we are saying when we say if a number is an integer, so if x is in Z, then it is rational. It is in Q. But x needs to have a domain. You can't just say if x is in something, then x is in something else, because what is x? We haven't defined it. We can't just throw in a variable that hasn't been declared. So oftentimes we will find that if we need to do implicit quantification, we'll just use an arrow, right? So in terms of notation, we often signify implicit quantification or implicit universal quantifiers as, and here's the way we're going to do it. We're going to say let P of x and Q of x be predicates and suppose the domain, and suppose they have a common domain of D. We're going to say P of x, and we have an arrow to Q of x, and that means that every element, so it implies, right? P of x implies Q of x, means that every element in the truth set of P of x is in the truth set of Q of x. Or for all x in domain D, that common domain D, I forgot to add that there, if P of x, then Q of x. And going back to our different kinds of statements from section 2.2, we have P of x, and with a double-headed arrow, Q of x, it means that P of x and Q of x have identical truth sets, or for all x in the common domain D, P of x if and only if Q of x. Those are our implicit universal quantifiers. How then do we determine the truth and false nature of these kinds of universal statements? Well, let's try one and see if we can figure it out. So let's look at example 3.1.3. A says, let our domain D be the set of integers 1, 2, 3, 4, and 5. No other integers, just those 5. 1, 2, 3, 4, and 5. So it says, let D be that set, and we're going to claim that for all x in our domain D, x squared is greater than or equal to x. So is this statement true or false? We want to use the method of exhaustion here, which means we have to find the truth values of each and every element. So we have to try each and every element in our predicate. So let's try it. So we're going to say let x equal 1. Then we're claiming that 1 is in our domain, which is true. And then if it is, then, oh, x squared is greater than or equal to x. So what is x squared? Well, x squared would be 1 squared, which is 1. Is 1 greater than or equal to 1, which is x? And the answer is yes. So we would say then x squared equals 1, and 1 is greater than or equal to 1. So this is true. Right? So this is true. Let's try it again. Now let's let x equal our next value, 2. Then what is 2 squared? Well, x squared then is 4. And 4 is still greater than or equal to 1 because we're looking at x squared being greater than or equal to 1. And we'll finish this out for x equals 3. Then 3 squared, right? X squared is 9. And 9 is certainly greater than or equal to 3. We would say let x equal 4. Then x squared equals 16. And 16 is certainly greater than or equal to 4. And for the last one, let x equal 5. Then x squared is greater than, is equal to 25. Let's make this one look more like equals. There we go. X squared equals 25, and 25 is greater than or equal to 5. So is this true for every element in D? And the answer is yes. We did not find a single counterexample. So we would say, therefore, the statement is true, right? So therefore, the statement is true. For all x in our domain, x squared is indeed greater than or equal to x. Well, let's change it a little bit. That one had a finite domain. Again, meaning it's small enough for us to count it. Finite means it's counted. There's a lot more to different kinds of ways to count, and If we have time, we'll get into that a little bit more. In chapter 5, we'll start talking about countable sets, and it's really a fascinating topic. But in this case, let's look at this infinite domain of the set of all real numbers. And we're still going to claim that for every x that is in that domain, so for every real number, its square is bigger than or equal to itself. Is this true or false? And we want to find a counterexample to show that it's false. We have lots and lots of options here. In fact, we have an infinite number of options because there's a very special set of numbers whose square is actually smaller than the number itself. And in one of my classes, they brought up the idea of 0.1 or 0.5, or if we thought of them as fractions, 1/10 or 1/2. So if we said, let's stick with 1/10 maybe, let x equal 1/10. Then x is a real number, and x squared is actually 1/10 divided by, or not divided by, sorry, 1/10 times 1/10 is 1/100. That's 0.01. So we would say, however, 1/100th, we'll just say, is not greater than or equal to 1/10. And therefore, the statement is false. If we wanted to do this with a separate example, we could say, let x equal, and we'll do it with a decimal this time. How about 0.2? Then we know that x is a real number, and x squared then would be 0.04. Remember, 0.2 would be 0.2 times 0.2. That's 2 times 2 is 4, and there are 2 decimal places, so you have to move it 2 decimal places to the left. Or you can use your calculator. So here, we have x squared is 0.04. However, 0.04 is not greater than or equal to 0.2. Therefore, the statement is false. You don't need more than one. I'm just giving you 2 options. You only need a single counterexample to show that a universal statement is false. Now that we've learned about the universal quantifier, let's talk about the existential quantifier. So the symbol that is a backwards E, I told you we have symbols for everything. We have abbreviations for everything. It means there exists and is called an existential quantifier. And in case you didn't know what existential means, it's referring to existing. So how do we use it? Well, let's start by looking at an example about books. I'm an avid reader. I love to read. I have a whole bunch of books on my bookshelves. So I said there is a book on my shelf that is a novel. How else could I write that? I could say there exists, right? There exists a book B on my shelf, right? There exists a book B on my shelf such that B is a novel. Okay, that works. There exists. There is a book B on my shelf such that B is a novel. Now, if we let S be the set of all books on my shelf, that's our domain, right? Is the set of all books on my shelf. We can now rewrite this symbol as there exists a book B in set S. There exists B in set S, the set of all books on my shelf, such that B is a novel. And something that you're going to notice is that we brought in a couple of words that we didn't have with universals. When we talk about existential, not only is there there exists, and there's something about our domain, right? And then there will be a such that. And then we'll get our predicate. Okay? There are multiple ways that I've seen such that written. I usually do s.t because we write it so very often. And again, as mathematicians, we love to abbreviate things. So we just write st, and the other way I've seen it is that element symbol just turned backwards. So sometimes people will write it as an element symbol just turned backwards. I don't tend to use that one as much because that wasn't the way I was taught how to write proofs. I was taught with just an s.t, so I teach it with an s.t. So when I start writing s.t, you'll know that means such that. So here, the domain of the predicate variable is generally indicated either between the there exists symbol and the variable name, or immediately following the variable name. The words such that are inserted just before the predicate. If we let Q of x be the predicate and D be the domain of x, then we can say that our existential statement then is a statement of the form there exists some x in domain D such that Q of x is true. It is defined to be true if and only if Q of x is true for at least one x in D, which means we only need one example. It is false if and only if Q of x is false for all of the elements in D. And so you're starting to see that there is definitely a relationship between the universal and existential quantifiers, very similar to the relationship between and or that we saw in logic. Because for a universal statement, it has to be true for all, and it only takes one counterexample to show that it's false. On the other side of that coin, you have a there exists, which only needs one example to show that it's true, but you have to show that it is false for every element. And we're going to find out in section 3.2 that is absolutely the case. That when you negate a universal statement, it becomes an existential statement. And when you negate an existential statement, it becomes a universal statement. So there is absolutely a relationship between these two, very similar to the one between and or. We're going to spend our time in this section on showing the truth of these statements, truth and false nature of the statements. We'll get into negations in the next section. All right, so let's see here. So let's consider some existential statements. If we consider the statement, there exists some m in the set of positive integers. Remember, z plus is positive integers, right? These will be our positive integers, such that m squared is equal to m. Is this statement true or false? There exists some m in the set of positive integers such that m squared equals m. So in the set of positive integers, 1, 2, 3, 4, 5, etc., we have an example of at least one number whose square is equal to itself. And I hope you figured out that m is 1. If we let m equal 1, then we know that m squared also equals 1, and m squared then equals m, right? So therefore, it is true that there exists some m in the set of positive integers such that m squared is equal to m. It is a true statement. Okay, that's not terrible. Let's try a couple more. Let's look at a finite domain for B. Let D, the domain, be the numbers 5, 6, 7, 8, and then consider the statement, there exists some M in the set D, or domain D, 5, 6, 7, 8, such that M squared is equal to M. Is our statement true or false? Well, let's try it. So let M equal 5. Then M squared equals 25. But 25 doesn't equal 5. Okay, that's all right. I only need one of them to work. Let M equals 6. Then M squared equals 36. But 36 doesn't equal 6. I'm having a bad feeling here. M equals 7. Let M equals 7. Then M squared equals 49. But 49 doesn't equal 7. Uh-oh, we got one more. Let M equal 8. Then M squared equals 64. But 64 doesn't equal 8. For our now finite domain, we don't have a single element that makes this statement true. In fact, all of them are false, which is our method of exhaustion. It relates right back to that universal quantifier where we use the method of exhaustion to show that the universal was true. We use the method of exhaustion to show that an existential statement is false. And in this case, we would say, therefore, it is false that there exists some M in our domain D such that M squared is equal to M. It is false. Let's try one more. We're going to go back to an infinite domain. Consider the statement, there exists some X in the set of real numbers. Remember, these are real numbers. Such that X squared is less than X. Is this statement true or false? I sure hope you can answer this because we already talked about it when we talked about our universal. We used this one as an example of how it wasn't true. But now we just said consider the statement that there exists some X instead of real numbers such that its square is less than itself. We know that one is true. We said let X equal, let's see, we did 1/10 and we did 0.2 for that one. Let's try 1/2. Let X equal 1/2. Then X squared equals 1/4. And 1/4 is indeed less than 1/2. Therefore, it is true that there exists some X in the set of real numbers such that X squared is less than X. And that's all the justification we need. And on our last page, we're going to talk about probably the most important kind of quantified statement that we're going to use in a proof writing class, and that is our universal conditional statement. So our universal conditional statement. And as it implies, we're going to be putting together a universal quantifier with a conditional statement. So we're putting the two together. So the quantifier from this section with the conditional statement from the last section. What does this look like? Well, we would say for all x in D, if P of x, then Q of x. Or if we would rather write it without the if and then, we can just use the implication symbol. For all x in D, if P of x, then Q of x. We're actually going to spend some time translating some statements we're going to prove into universal conditional statements. So we're going to do that at another time, closer to when we are taking our exam for this unit. But that's going to come up in a little while. We're going to talk about that. So for now, let's try to figure out how these work. So in example 3.1.5, we wanted to determine the truth and falsity of universal conditional statements. Consider the statement for all x in a set of integers, if x is even, then x squared is even. Is this statement true or is it false? Well, this is kind of going to bring us into a little bit of a preview of what we're going to be doing in chapter 4. We have to consider, what does it mean to be even? And a lot of times students will tell me, well, it's divisible by 2. And what you're going to find is that in discrete math, we don't talk about division exactly, we talk about divisibility, meaning it could be divided. So what we would say is that x needs to be an integer, and we need to say that x squared means that x is multiplied by x. And an even number multiplied by an even number is still even. And we can say that because every even number is a multiple of 2. We have multiple ways we can do this, and we're going to find better ways to show that this is true. And you can see where things get very complicated when we get onto an infinite domain, because now we need proof writing skills. So we're going to try to get around it just a little bit by saying, let's let x be an integer, right? But let's let x be an even integer at that. So it's an even integer. Notice what I'm not doing is arguing from one specific example. We can't just use 2, and 2 squared is 4, or 4, and 4 squared is 16. We're trying to claim it for every single even integer. So if we let x be any even integer, just an even integer, then we know that x squared is x multiplied by x. And an even number, right? An even number multiplied by another even number is also even. So we're going to lean into some of the things we already know about numbers. We're going to find a better way to do this in chapter 4, because we will define an even number as 2 times some other integer. Every even number is 2 times another integer. So we'll get to that, okay? And so they would say, then, therefore, this statement here is true. But if I let's look at part B. If I let C be the set of students in our class, and I said, for all C in the set of students in our class, if C is missing from class, then C has contracted COVID-19. Is this statement true or false? Well, all you have to do is just pick a student who missed a class and didn't have COVID. And so then you could prove that our statement was false. It's a single counterexample. So I'm going to say, let Kira be a student in our class, right? Kira missed class, right, for a doctor's appointment. Oops, there's only 2 P's in appointment. Let's try that again. For a doctor's appointment. Therefore, it is false to claim that she has COVID. And then the statement is false. So, to give you an idea of what our universal statements are going to look like as we move forward, let's say something like the sum of an even number and an odd number is odd. And we want to convert that to a universal conditional statement. We don't have to know the definitions of even and odd yet. We're going to get there in a couple weeks. It's going to be the first definition we learn with proofreading. We're going to learn about evens and odds first. But for now, we want to talk about the sum of an even number and an odd number is odd. So how would we convert this to a universal conditional? How do we even know it's universal? It says the sum of an even number and an odd number. That's our only indication, really. So we have to say for all something. Well, it turns out that even numbers and odd numbers are also integers. So we have multiple numbers here. We have an even number, which we'll call that one. Our even number we'll call M, and our odd number we'll just call N. And they have to be different variables because if I did M for even and M for odd, then you're trying to say one number is both even and odd. And we all know that's not true. Even zero is only even. So that's not going to work. So we have to have an M and an N. So we would just say for all M and N in a set of integers, if M is even and N is odd, then what are we claiming about their relationship? We're claiming then that M plus N is odd. That's how we would rewrite this as a universal conditional statement. We'll look at a few more when we get back to class and try those before we move on to our next section. And we'll practice a little bit more while we're reviewing for the exam. And then we're going to have to jump in with both feet writing out our proof statements in this manner when we get into chapter 4 and starting to write proofs.